Hello everyone. So we are posting class 12 audiobooks for physics. So this is the first time on YouTube that we are posting audiobooks for physics. So please do give it a thumbs up and please do subscribe our channel for more contents. So let's start. Chapter 3 Current Electricity 3.1 Introduction. In Chapter 1, all charges were free or bound, were considered to be at rest. Charges in motion constitute an electric current. Such currents occur naturally in many situations. Lightning is one such phenomenon in which charges flow from one cloud to the earth through the atmosphere, sometimes with disastrous results. The flow of charges in lightning is not steady, but in our everyday life we see many devices where charges flow in a steady manner, like water flowing smoothly in a river. A torch and a cell-driven clock are examples of such devices. In present chapter, we shall study some of the basic laws concerning steady current electrics. 3.2 Electric current. Imagine a small area held normal to the direction of flow of charges. Both the positive and the negative charges may flow forward and backward across the area. In a given time interval small t, let q plus be the net amount, that is forward minus backward, of the positive charge that flows in the forward direction across the area. Similarly, let q minus be the net amount of the charge negative flowing across the area in forward direction. Let the net amount of charge flowing across the area in the forward direction in the time interval t is q is equal to q plus minus q minus. This is proportional to t for steady current, and the quotient I is equal to q by t is defined to be the current across the area in forward direction. If it turn out to be a negative number, it implies a current in the backward direction. Currents are not always steady, and hence more generally we define the current as follows. Let delta q be the net charge flowing across a cross section of the conductor during the time interval delta t, that is between time t and t plus delta t. Then the current at a time t across the cross section of the conductor is defined as the value of the ratio of delta q to delta t in limit of delta t tending to 0. That is, I of t is equal to limit delta t tends to 0 delta q by delta t. In SI units, the unit of current is ampere. An ampere is defined through magnetic effects of currents that we will study in the following chapter. An ampere is typically the order of magnitude of currents in domestic appliances. An average lightning carries current of order of tens of thousands of amperes, and at the other extreme, currents in our nerves are in microamperes. 3.3 Electric current in conductors. An electric charge will experience a force if an electric field is applied. If it is free to move, it will thus move, contributing to a current. In nature, free charged particles do not exist like in upper strata of atmosphere called the ionosphere. However, in atoms and molecules, the negatively charged electrons and the positively charged nuclei are bound to each other and are thus not free to move. Bulk matter is made up of many molecules. A gram of water, for example, contains approximately 10 raised to 22 molecules. These molecules are so closely packed that the electrons are no longer attached to individual nuclei. In some materials, the electrons will still be bound, that is, they will not accelerate even if the electric field is applied. In other materials, notably metals, some of the electrons are practically free to move within the bulk material. These materials, generally called conductors, develop electric currents in them when an electric field is applied. If we consider solid conductors, then of course the atoms are tightly bound to each other so that the current is carried by negatively charged electrons. There are, however, other types of conductors like electrolytic solutions where positive and negative charges both can move. In our discussions, we will focus only on solid conductors so that the current is carried by the negatively charged electrons in the background of fixed positive ions. Consider first the case when no electric field is present. The electrons will be moving due to thermal motion during which they collide with the fixed ions. An electron colliding with an ion emerges with the same speed as before the collision. However, the direction of its velocity after the collision is completely random. At a given time, there is no preferential direction for the velocities of the electrons. Thus, on the average, the number of electrons traveling in any direction will be equal to the number of electrons traveling in the opposite direction. So, there will be no net electric current. Let us now see what happens to such a piece of conductor if an electric field is applied. To focus our thoughts, imagine the conductor in the shape of a cylinder of radius capital R. See figure 3.1. Suppose we now take two thin circular discs of a dielectric of the same radius and put positive charge plus Q distributed over one disc and similarly minus Q at the other disc. We attach the two discs on the two flat surfaces of the cylinder. An electric field will be created and is directed from the positive towards the negative charge. The electrons will be accelerated due to this field towards plus Q. They will thus move to neutralize the charges. The electrons, as long as they are moving, will constitute an electric current. Hence, in the situation considered, there will be a current for a very short while and no current thereafter. We can also imagine a mechanism where the ends of the cylinder are supplied with fresh charges to make up for any charges neutralized by electrons moving inside the conductor. In that case, there will be a steady electric field in the body of the conductor. This will result in continuous current rather than a current for a short period of time. Mechanisms which maintain a steady electric field are cells or batteries that we shall study later in this chapter. In the next sections, we shall study the steady current and that results from a steady current field in conductors. 3.4 Ohm's Law. A basic law regarding flow of currents was discovered by George Simon Ohm in 1828, long before the physical mechanism responsible for flow of currents was discovered. Imagine a current conductor through which a current I flowing and let V be the potential difference between the ends of the conductor. Then Ohm's law states that V directly proportional to I or V is equal to Ri, where constants of proportionality R is called resistance of the conductor. The SI units of resistance is ohm and is denoted by symbol omega. The resistance R not only depends on the material of the conductor but also on the dimensions of the conductor. The dependence of R on the dimensions of the conductor can easily be determined as follows. Consider a conductor satisfying equation V is equal to IR to be in the form of a slab of length L and cross-sectional area A. Imagine placing two such identical slabs side by side so that the length of the combination is 2L. The current flowing through the combination is the same as that flowing through the either of slabs. If V is the potential difference across the ends of the first slab, then V is also the potential difference across the ends of the second slab, since the second slab identical to the first slab and the same current I flows through the both. The potential difference across the ends of the combination is clearly the sum of the potential differences across the two individual slabs and hence equals 2V. The current through the combination is I and the resistance of the combination is RC is. RC is equal to 2V divided by I is equal to 2R. Since V by I is equal to R, the resistance of either of the slabs, thus doubling the length of conductor doubles the resistance. In general, the resistance is proportional to length R directly proportional to L. Next, imagine dividing the slab into two by cutting it lengthwise. On that, the slab can considered as a combination of two identical slabs of length L, but each having a cross-sectional area A by 2. For a given voltage V across a slab, if I is the current through the entire slab, then clearly the current flowing through each of the two half slabs is I by 2. Since the potential difference across the ends of the half slabs is V, that is the same as across the full slab, the resistance of each of the half slab R1 is equal to V by I by 2 equals to 2 into V by I is equal to 2R. Thus, halving the area of the cross-section of a conductor doubles the resistance. In general, then the resistance R is inversely proportional to cross-sectional area. R is inversely proportional to area. Combining equations, we have R directly proportional to L by A, and hence for a given conductor R equals to rho L by A, where the constant of proportionality rho depends on the material of the conductor but not on its dimensions. Rho is called resistivity. Using the last equation, Ohm's law reads like V is equal to I into R is equal to I rho L by A. Current per unit area taken normal to the current is equal to I by A is called current density and is denoted by small letter j. The SI unit of current density are ampere per meter square. Further, if electric field is E is the magnitude of uniform electric field in the conductor whose length is L, then the potential difference V across its ends is E into L. Using these, the last equation reads E into L is equal to J rho L. E is equal to rho J. The above relation of magnitudes E and J can indeed be cast in a vector form. The current density, which we have defined as the current through unit area normal to the current, is also directed along E and is also a vector. J is equal to J vector divided by magnitude of E. Thus, the last equation can be written as E is equal to J rho. J is equal to sigma E, where sigma is equal to 1 by rho is called the conductivity. Ohm's law is often stated in an equivalent form, equation 3.13, in addition to equation 3.3. In the next session, we will try to understand the origin of the Ohm's law as arising from the characteristics of the drift of electrons. 3.5 Drift of electrons and the origin of resistivity. As remarked before, an electron will suffer collisions with the heavy fixed ions, but after collision it will emerge with the same speed but in random directions. If we consider all the electrons, either average velocity will be 0 since the directions are random. Thus, if there are n electrons and the velocity of the ith electron I is equal to 1, 2, 3, 4, etc. n at a given time is Vi, then 1 by n summation I is equal to 1 to n, Vi is equal to 0. Consider now the situation when an electric field is present. Electrons will be accelerated due to the field by A is equal to minus E by m, minus small e capital E divided by m, where minus small e is the charge and m is the mass of an electron. Consider again the ith electron at a given time t. This electron would have had its last collision sometime before t, and let ti be the time elapsed after its last collision. If Vi was velocity immediately after the last collision, then its velocity Vi at time t is Vi is equal to Vi plus minus small e capital E divided by m into Ti. Since starting with its last collision it was accelerated with an acceleration given by equation 3.15 for a time interval Ti, The average velocity of the electrons at time t is the average of all the VIs. The average of VIs is 0. Since immediately after any collision, the direction of the velocity of an electron is completely random. The collisions of the electrons do not occur at regular intervals but at random times. Let us denote by tau the average time between successive collisions. Then at a given time, some of the electrons would have spent time more than tau and some less than tau. In other words, the time Ti in equation 3.16 will be less than tau for some and more than tau for others. We go through the values of I is equal to 1 to etc. n. The average value of Ti then is tau, known as relaxation time. Thus, averaging equation over the n electrons at any given time t gives us the average velocity Vd. Vd is equal to Vi average is equal to V small I average is equal to minus E by m into Ti average is equal to 0 minus E tau by m is equal to minus E capital E tau divided by m is equal to Vd. This last result is surprising. It tells us that the electrons moving with average velocity which is independent of time, although electrons are accelerated. This is the phenomenon of drift, and the velocity Vd is called the drift velocity. Because of the drift, there will be net transport of charges across any area perpendicular to E. Consider a planar area A allocated inside the conductor such that the normal to the area is parallel to E. Then because of the drift in an infinitesimal small amount of time, delta t, all electrons to the left of the area at a distances up to modulus Vd into delta t would have crossed the area. If n is the number of free electrons per unit volume in the metal, then there are n into delta t into modulus Vd into a such electrons. Since each electron carries a charge minus E, the total charge transported across the area A to right in time delta t is minus NEA V delta t. E is directed towards the left and hence the total charge transported along E across the area is negative of this. The amount of charge crossing the area A in time delta t is by definition I into delta t, where I is the magnitude of the current. Hence, Q is equal to IT, we know that. So, I into delta t is equal to plus NEA modulus Vd into delta t. Substituting the values of modulus Vd from equation 3.17, we get I into delta t is equal to E square A divided by M tau n delta t into modulus E. By definition, I is related to magnitude of J of the current density by I is equal to JA. Hence, from equations, we get modulus J is equal to NE square by M into tau into modulus of E. The vector J is parallel to E, and hence we can write equation 3.21 in the vector form like J is equal to NE square tau E by M. Comparison with equation 3.13 shows that equation 3.22 is exactly the Ohm's law if we identify the conductivity sigma as sigma is equal to NE square tau by M. We thus see that very simple picture of electrical conduction reproduces Ohm's law. We have of course made assumptions that tau and n are constants independent of electric field. We shall in the next section discuss the limitation of Ohm's law. Limitations of Ohm's law 3.6. Although Ohm's law has been found valid over a large class of materials, there do exist materials and devices used in electric circuits where the proportionality of V and I does not hold. The deviations broadly are one or more of the following types. A. V ceases to be proportional to I. B. The relation between V and I depends on the sign of V. In other words, if I is the current for certain V, then reversing the direction of V, keeping its magnitude fixed, does not produce a current of the same magnitude as I in the opposite direction. This happens, for example, in a diode, which we will study in chapter 14. Figure 3.6, characteristic curve of a diode. Note the different scales for negative and positive values for the voltage and current. Figure 3.7, variation of current versus voltage for gallium arsenide semiconductor device. There we can see a nonlinear region and a negative resistance region. C. The relation between V and I is not unique. That is, there is more than one value for V for the same current I. A material exhibiting such behavior is gallium arsenide. Materials and devices not be obeying Ohm's law in the form of equation 3.3 are actually widely used in electronic circuits. In this and a few subsequent chapters, however, we will study the electrical currents in materials that obey Ohm's law. Metals have low resistivities in the range of 10 raised to minus 8 ohm meter to 10 raised to minus 6 ohm meter. At the other end are insulators like ceramic, rubber and plastics having resistivities 10 raised to 18 times greater than metals or more. In between the two are the semiconductors. These, however, have resistivity characteristically decreasing with a rise in temperature. The resistivities of semiconductors are also affected by presence of small amounts of impurities. This last feature is exploited in use of semiconductor for electronic devices. 3.8, temperature dependence of resistivity. Rho T is equal to rho 0 into 1 plus alpha into T minus T0, where rho T is the resistivity at the temperature T and rho 0 is the same at a reference temperature T0. Alpha is called the temperature coefficient of resistivity, and from equation 3.26 above, the dimension of alpha is, that is, temperature raised to minus 1 for metals is positive. The relation of equation 3.26 implies that a graph of rho T plotted against T would be a straight line. At temperatures much lower than 0 degree, the graph, however, deviates considerably from a straight line. Equation 3.26 thus can be used approximately over a limited range of T around any reference temperature T0, where the graph can be approximated as a straight line. Figure 3.8, resistivity rho T of a copper as a function of temperature T. You can see the graph is an increasing curve. Figure 3.9, resistivity rho T of nichrome as a function of absolute temperature T. You can see the graph is a straight line, not starting from the origin. Figure 3.10, temperature dependence of resistivity for a typical semiconductor or an insulator. You can see the graph is again a rectangular hyperbola. Some materials like nichrome, which is an alloy of nickel, iron and chromium, exhibit a very weak dependence of resistivity with temperature. Manganese and constantan have similar properties. These materials are thus widely used in wire-bound standard resistors, since their resistances values would change very little with the temperature. Unlike metals, the resistivities of semiconductor decreases with increase in temperatures. A typical dependence is shown in figure 3.10. We can qualitatively understand the temperature dependence of resistivity in the light of our derivations of equation 3.23. From this equation, rho is equal to, that is resistivity, is equal to 1 by sigma is equal to m by ne square tau. Rho thus depends inversely on both the number of free electrons per unit volume n and on the average time tau between the collisions. As we increase temperature, average dependence of the electrons which act as carriers of current increases, resulting in more frequent collisions. Average time of collision tau thus decreases with the temperature. In a metal, N is not dependent on temperature to any appreciable extent, and thus the decrease in the value of tau will, with the increase in temperature, causes rho to increase as we have observed. For insulators and semiconductors, however, N increases with temperature. This increase more than compensates any decrease in tau in equation 3.23, so that for such materials rho decreases with the temperature. 3.9 Electrical energy power. Consider a conductor with endpoints A and B in which a current I is flowing from A to B. The electric potential at A and B are denoted by VA and VB respectively. Since current is flowing from A to B, VA is greater than VB and the potential difference across AB is V is equal to VA minus VB greater than 0. In a time interval delta t, an amount of charge delta Q is equal to IT travels from A to B. The potential energy of the charge at A by definition was Q VA, and similarly B is Q into VB. Thus change in potential energy delta U potential is delta U potential energy is equal to final potential energy minus initial potential energy is equal to delta Q into VB minus VA is equal to minus delta Q into V is equal to minus I V delta T less than 0. If charges moved without collisions through the conductor, their kinetic energy would also change so that the total energy is unchanged. Conservation of total energy would then imply that delta K is equal to minus delta U potential energy. That is delta K is equal to I V delta T greater than 0. Thus, in case charges were moving freely through the conductor under the action of electric field, their kinetic energy would increase as they move. We have, however, seen earlier that on average, charge carriers do not move with acceleration but with a steady drift velocity. This is because of the collision with ions and atoms during transit. During collisions, the energy gained by the charges thus is shared with the atoms. The atoms vibrate more vigorously, that is, the conductor heats up. Thus, an actual conductor, an amount of energy dissipated as heat in the conductor during the time interval delta T is delta W is equal to I V delta T. The energy dissipated per unit time is the power dissipated. P is equal to delta W by delta T, and we have P is equal to IV. Using Ohm's law, V is equal to IR, we get P is equal to I square R is equal to V square by R. As the power loss, that is ohmic loss, in a conductor of resistance R carrying a current I, it is this power which heats up, for example, the coil of an electric bulb to incandescence, radiating out heat and light. Where does the power come from? As we have reasoned before, we need an external source to keep a steady current through the conductor. It is nearly this source which must supply this power. In simple circuits shown with a cell, it is the chemical energy of the cell which supplies this power for as long as it can. The expressions for power, equations 3.32 and 3.33 shows the dependence of the power dissipated in resistance R on the current through it and the voltage across it. Okay. Equations 3.33 has an important application to power transmission. Electrical power is transmitted from power stations to homes and factories, which may be hundreds of miles away via transmission cables. One obviously wants to minimize the power loss in the transmission cable connecting the power stations to home and factories. We shall see now how this can be achieved. Consider a device R to which a power P is to be delivered via transmission cables having a resistance RC to be dissipated by it finally. If V is the voltage across R and I is the current through it, then P is equal to VI. The connecting wires from the power station to the device has a finite resistance RC. The power dissipated in the connecting wires which is wasted is PC, with PC is equal to I square RC is equal to P square RC divided by V square. From equation 3.32, thus to drive a device of power P, the power wasted in the connecting wire is inversely proportional to the V square. The transmission cables from power stations are hundreds of miles long and their resistance RC is considerable. To reduce PC, these wires carry current at enormous values of V, and this is the reason for high voltage danger signs on transmission lines, a common sight as we move away from populated areas. During electricity at such voltage is not safe, and hence at other end a device called a transformer lowers the voltage to value suitable for use. 3.10 Cells EMF internal resistance. We have already mentioned that a simple device to maintain a steady current in an electric circuit is the electrolytic cell. Basically, a cell has two electrodes called the positive and the negative, denoted as P and N, as shown in figure 3.12. They are immersed in an electrolytic solution. Dipped in the solution, the electrodes exchange charges with the electrolyte. Positive electrode has a potential difference of V plus greater than 0 between itself and the electrolyte solution immediately adjacent to it, marked A in the figure. Similarly, negative electrode develops a negative potential minus V minus, that is V minus greater than 0 relative to the electrolyte adjacent to it, marked as B in the figure. When there is no current, the electrolyte has the same potential throughout, so that the potential difference between P and N is V plus minus minus V minus, that is V plus plus V minus. This difference is called the electromotive force or EMF of the cell and is denoted by epsilon. Thus, epsilon is equal to V plus plus V minus greater than 0. Note that E is, or epsilon is, actually a potential difference and not a force. The name EMF, however, is used because of historical reasons and was given at a time when the phenomenon was not understood properly. To understand the significance of epsilon, consider a resistor R connected across the cell. A current I flows across R from C to D. As explained before, steady current is maintaining because current flows from N to P through the electrolyte. Clearly, across the electrolyte, the same current flows through the electrolyte from N to P, whereas through R it flows from P to N. The electrolyte through which a current flows has a finite resistance R called the internal resistance. Consider first the situation when R is finite, so that I is equal to V by R is equal to 0, where V is the potential difference between P and N. Now V is equal to potential difference between P and A plus potential difference between A and B plus potential difference between B and N. is equal to EMF. Thus, EMF is the potential difference between the positive and the negative electrodes in an open circuit, that is, when no current is flowing through the cell. If, however, R is finite, I is not 0. In that case, potential difference between P and N is V is equal to V plus V minus IR is equal to EMF minus IR. So, V is equal to E minus IR. Note the negative sign in the expression IR for the potential difference between A and B. This is because the current I flows from A to B in the electrolyte. In practical calculations, internal resistance of cells in the circuit may be neglected when the current I is such that E is very much greater than IR. The actual value of the internal resistance of cell vary from cell to cell. Internal resistance of dry cells is much higher than the common electrolytic cells. We also observe that since V is the potential difference across R, we have Ohm's law as V is equal to IR. Combining equations, we get IR is equal to E minus IR, or IR is equal to E by capital R plus R. The maximum current that can be drawn from a cell is for R is equal to 0, and it is I max is equal to E by R. However, in most cells, the maximum allowed current is much lower than this to prevent permanent damage to the cell. Like cells in series and in parallel. Like resistors, cells can be combined together in an electric circuit. And like resistors, one can, for calculating currents and voltages in a circuit, replace a combination of cells by equivalent cell. Figure 3.20, two cells of EMF E1 and E2 in the series R1 R2 are their internal resistances for connections across A and C. The combination can be considered as one cell of EMF EQ, E equivalent, and an internal resistance of R equivalent. Consider the first two cells in figure 3.13, where one terminal of the two cells is joined together, leaving other terminal in the either cell free. E1, E2 are the EMFs of the two cells, and R1, R2 are the internal resistances respectively. Let VA, VB, VC be the potentials at point A, B, C shown figure 3.20. Then VA minus VB is the potential difference between the positive and the negative terminals of the first cell. We have already calculated it in equation 3.37, and hence VAB is equal to VA minus VB is equal to E1 minus IR1. Similarly, VBC is equal to E2 minus IR2. Hence, potential difference between the terminals A and B of the combination is VAC is equal to VA minus VC is equal to VA minus VB plus VB minus VC. So VB and minus VB get cancelled, so you will get VA minus VC is equal to E1 plus E2 minus I into R1 plus R2. If we wish to replace the combination by a single cell between A and of EMF E equivalent and internal resistance R equivalent, we would have VAC is equal to E equivalent minus I R equivalent. Comparing the last two equations, we get E equivalent is equal to E1 plus E2 and R equivalent is equal to R1 plus R2. In figure 3.20, we had connected the negative electrode of the first to positive electrode of the second. If instead we connect two negatives, equation 3.42 would change to VBC is equal to minus E2 minus R2, and we will get E equivalent is equal to E1 minus E2 when E1 is greater than E2. The rule for series combination clearly can be extended to any number of cells. 1. The equivalent EMF of a series combination of n cells is just the sum of their individual EMFs. And 2. The equivalent internal resistances of a series combination of n cells is just the sum of their internal resistances. This is so when the current leaves such each cells from the positive electrode. If in the combination the current leaves any cell from the negative electrode, EMF of the cell enters the expression for E equivalent with a negative sign as in equation. Next, consider a parallel combination of cells. I1 and I2 are the current leaving the positive electrodes of the cells. At the point B1, I1 and I2 flow in whereas current I flows out. Since as much charge flows in as out, we have I is equal to I1 plus I2. Let VB1 and VB2 with the potentials at B1 and B2 respectively. Then considering the first cell, potential difference across its terminals is VB1 minus VB2. Hence from equations 3.38, V is equal to VB1 minus VB2 is equal to epsilon 1 minus IR1. Points B1 and B2 are connected exactly similar to the second cell. Hence, considering the second cell, we also have V is equal to VB1 minus VB2 is equal to E2 minus I2R2. Combining the last three equations, I is equal to I1 plus I2 plus E1 minus V by R1 is equal to E2 minus V by R2 is equal to what? Is equal to E1 by R1 plus E2 by R2 minus V into 1 by R1 plus 1 by R2. Hence, V is given by E1 R2 plus E2 R1 divided by R1 plus R2 minus I into R1 R2 divided by R1 plus R2. If we want to replace the combination by a single cell between B1 and B2 of EMS E equivalent and internal resistance R equivalent, we would have V is equal to E equivalent minus I R equivalent. The last two equations should be the same, and hence E equivalent is equal to E1 R2 plus E2 R1 divided by R1 plus R2, and R equivalent is equal to R1 R2 divided by R1 plus R2. We can put these equations in a simpler way, that is 1 by R equivalent is equal to 1 by R1 plus 1 by R2. E equivalent by R equivalent is equal to E1 by R1 plus E2 by R2. In figure 3.14, we had joined the positive terminals together and similarly the two negative ones so that the currents I1, I2 flow out of positive terminals. If the negative terminal of the second is connected to the positive terminal of the first, that is equations 3.56 and 3.57 would still be valid with E2 tends to minus E2. Equations can be extended easily if there are n cells of EMF E1 etc. En and of internal resistances R1, R2 etc. Rn respectively connected in parallel. The combination is equivalent to a single cell of EMF E equivalent and internal resistance R equivalent such that 1 by R equivalent plus 1 by R1 is equal to 1 by equivalent R equivalent is equal to 1 by R1 plus 1 by R2 etc. 1 by Rn. So E equivalent divided by R equivalent plus is equal to E1 by R1 plus E2 by R2 etc. En by R1. 3.12 Kirchhoff's rules. Electric circuits generally consist of a number of resistors and cells interconnected, sometimes in a complicated way. The formulae we have delivered earlier for series and parallel combination of resistors are not always sufficient to determine all the currents and potential differences in the circuit. Two rules called Kirchhoff's rules are very useful for analysis of electric circuits. Given a circuit, we start by labeling currents in each resistor by a symbol say I and a directed arrow to indicate that current I flows along the resistor in the direction indicated. If ultimately I is determined to be positive, the actual current in the resistance is the direction of the arrow. If I turns out to be negative, then the current actually flows in a direction opposite to the arrow. Similarly, for each source, that is cell of some other source of electrical power, the positive and the negative electrodes are labeled, as well as a directed arrow with a symbol for the current flowing through the cell. This will tell us the potential difference. V is equal to Vp minus Vn is equal to E minus IR. Equation 3.38 between the positive terminals P and the negative terminals N. I here is the current flowing from N to P through the cell. If while labeling the current I through the cell 1 goes from P to N, then of course V is equal to E plus IR. Having clarified labeling, we now state the rules and the proof. A. Junction rule. At any junction, the sum of the currents entering the junction is equal to the sum of the currents leaving the junction. This applies equally well if instead of a junction of several lines, we consider a point in a line. The proof of this rule follows from the fact that when currents are steady, there is no accumulation of charges at any junction or at any point in a line. Thus, the total current flowing in, which is the rate at which charge flows into the junction, must be equal to the total current flowing out. 2. Loop rule. The algebraic sum of changes in potential around any closed loop involving resistors and cells in the loop is 0. This rule also obvious since electric potential is dependent on the location of the point. Thus, starting with any point, we come back to the same point. The total change must be 0. In a closed loop, we do come back to the starting point and hence the rule. It should be noted that because of the symmetry of the network, the great power of Kirchhoff's rule has not been very apparent in example 3.5 above. In a general network, there will be no such simplification due to symmetry, and only by application of Kirchhoff's rule to junctions and closed loop as many as necessary to solve the unknowns in the network can we handle the problem. This will be illustrated in example 3.6. 3.13 Wheatstone Bridge. As an application of Kirchhoff's rule, consider the circuit shown in figure 3.18, which is called a Wheatstone bridge. The bridge has 4 resistors R1, R2, R3 and R4 across one pair of diagonally opposite points A and C in the figure. A source is connected. This, that is AC, is called a battery arm. Between the other two vertices B and D, a galvanometer G, which is a device to detect current, is connected. This line shown as BD in the figure is called the galvanometer arm. For simplicity, we assume that the cell has no internal resistance. In general, there will be currents flowing across the resistors as well as a current Ig through G. Of special interest is the case of a balanced bridge where the resistors are such that Ig is equal to 0. We can easily get the balance condition such that there is no current through G. In this case, the Kirchhoff's junction rule applied to junctions D and B immediately gives the relation I1 is equal to I3 and I2 is equal to I4. Next, we apply Kirchhoff's loop rule to closed loops A, D, B, A. See the figure, and C, B, D, C. The first loop gives minus I1 R1 plus 0 plus I2 R2 equal to 0, where Ig is equal to 0, and the second loop gives upon using I3 is equal to I1, I4 is equal to I2, I2 R4 plus 0 minus I1 R3 is equal to 0. From equations we obtain that I1 by I2 is equal to R2 by R1, whereas from equation 3.63 we obtain that I1 by I2 is equal to R4 by R3. Therefore, we obtain the condition as R2 by R1 is equal to R4 by R3. This last equation relating the four resistance is called the balance condition for galvanometer to give zero or null deflection. The Wheatstone bridge and its balance condition provide a practical method for determination of an unknown resistance. Let us suppose we have an unknown resistance which we insert in the fourth arm. R4 is thus not known. Keeping known resistances R1 and R2 in the first and second arm of the bridge, we go on varying R3 till the galvanometer shows a null diffraction. The bridge then balanced, and from the balance condition the value of the unknown resistance R4 is given by R4 is equal to R3 into R2 by R1. A practical device used in this principle is called a meter bridge. It will be discussed in the next session. So that's all for this whole chapter, NCRT. So everybody, please do like this video and please do subscribe the channel, because we are putting a lot of effort in making these NCRT capsule videos for you. So please do subscribe, and please do comment your valuable comments in the chat box, so that I'll get a motivation to post other chapters too. So thanks for watching. Take care and bye.